Hello, we are graduate students from University of Tokyo. Very glad to be here today. We study ocean technology and environment. Presenters are Wataru Fujimoto and Kosuke Makino. Now let's start. Have you ever imagined the world of 50-meter deep ocean? There massive flow exists called ocean current. Our vision is to generate ocean electricity from ocean current and contribute to solution of energy problem. In this presentation, we propose a system that utilizes the giant current with floating turbine and mooring line, like kites. Ocean currents are global seawater flow. Kuroshio and Gulf Stream are very famous. Kuroshio flows near Japan and around Taiwan. Why do we focus on ocean currents? They have two advantages. First, ocean currents are more constant and reliable. Capacity factor of winds or solar power is very low because they cannot generate in the day of no wind days and cloudy days. But ocean current power have high capacity factor. Ocean currents flows every day and every time, and they are little affected in the waves. So ocean currents are very stable, and they don't need difficult grid control technology and large power backup. That is big problem for solar and wind. Second advantage is high energy density. This figure shows ocean current power have higher energy density than wind. We can gain high energy with small turbine and reduce cost of materials. These two advantages lead to feasibility of ocean currents. Power cost of Kuroshio is lower than that of offshore wind or photovoltaic power. So we consider ocean current power is very promising. To commercialize ocean current power, two challenges we had. First challenge is decreasing generator cost, and second challenge is increasing current energy. First, we try to design simpler and lighter generator. Then let's think how to build a generator in ocean currents. How about the generator like conventional wind turbines? In location of ocean current, the depth to the seabed is 1,000 meters, so tower is too long. Let's attach the mooring line. And ocean currents has high energy density, so short turbine is enough. It seems very nice, but two big problems exist. First, when turbines start rotating, torque load on the generator pod, and pod also rotates. In this situation, generator cannot work efficiently. Second, position deviation caused from change of ocean current, and large stress load on the mooring line, and it will fatigue. These two problems were our main task. For first problem, cancelling torque, two main type generator were designed. First is twin turbine type. Two couples of turbines rotating around two axes in opposite direction each other, and the total torque on whole structure is zero. The other type have additional components to stop generator rotating, but this additional structure leads to increased generator cost. So, we propose unique and innovative concept, control rotating turbine system. Two couples of turbine rotates around one axis in opposite direction each other and cancel torque. This system is simpler and lighter, and we can reduce cost of materials 30% from previous model.
So far, my teammate Wataru explained you how attractive ocean current is and how to settle the first issue to realize simpler and lighter structure. And now, I'd like to talk about the second issue, position deviation. Position deviation occurs when ocean current changes. However, we have to control the generator's position to stable and normal position. Then, we got the hint from helicopter, which also has control rotating system. We'd like to apply this controlling system to our generator's turbine. This system is by changing turbine's angle of attack, and we can change the force applied to each turbine. And then we can control the position to stable and normal position. So with these technologies, we can realize simpler and lighter structure. And next issue is proof of our concept. We conducted both numerical simulation and tank experiment to validate this our innovative and unique concept. So here is tank experiment videos. I'd like you to focus on two important points. First is no-pot rotations, and second point is position controlling. Then, let's see. No-pot rotates because of control rotating system, and by changing turbine's angle of attack, we can change the position of generator. And also, this result is highly fitting with our numerical simulations result. So, generator is moving as we expect. So we got the control of generator. So far, to reduce generator's cost, we proposed unique and simple concept and showed you its technological feasibility of active controlling system. Then the other issue to reduce power cost is how to maximize production from ocean current energy. This means how to identify the best site for deployment. To answer this issue, we have to know the position of ocean current in detail. And our downscaling model can answer this issue. This is typical model which has 10-kilometer grid resolution. And focusing on this area, please find the best location for deployment. Well, this is very difficult, just like finding your home from national map. However, we need local map. So, take a look at our high-resolution map. With our downscaling technology, we can figure out where on Earth strong current exists in detail. So, we know the position of ocean current in detail. So, this is a summary of our innovative technology set to make system competitive and to reduce power cost. And to reduce generator cost, we proposed simple and light structure and showed you its technological feasibility of active controlling system. And to maximize power gain from ocean current, we developed downscaling model, which allows us to identify the best point of deployment. So, we are ready for field experiment in the ocean as the next step. Let's make sustainable society with ocean current energy and our unique technology set. Okay. Thank you for your kind attention.
You compared power cost to PV and offshore wind.
Yeah.
Okay, but these two has a long track of realistic data.
Yeah.
What kind of data do you have for the power cost of this ocean current power?
Thank you very much. That's a very good question. As you can see, the study of ocean current energy is still in the early stage of research and development. So most of them are from guesses, but we have analytical study from offshore wind turbines and like, for example, sending electricity to land, we can use the figures from offshore wind energy. And most of the structure is analogical to wind powers. So like the power generation system, the blade system, all of them, the figures of the cost can be estimated from those realistic numbers. But as you have mentioned, what we have made is still a 1/50th scale model. So we should improve our estimation.
How do you solve this biological fouling problems?
Thank you. Another very good question. We are trying to use the technology that has been already developed in shipbuilding industry. So the bottom of the ships have faced the same problem. And for those problems, the shipbuilding industry have coatings for the bottom of the ship to prevent biofoulings. And we're trying to do the same thing. Actually, we're working with heavy industry people to develop this system.
They still have the change about the security and the safety for the structure. Yeah. So how do you do this?
So
The safety and the security and the stability of the structure in the ocean. Yeah.
Yes, that's an important point that we have to work on from now. Actually, we've been working on tank experiments, which has we can control the flow. We can artificially change it, but we just impose the current that we want. And as he mentioned at last, we're going to have an ocean field experiment from this September, and there we will have some other current variation that we have not we may not have even thought of. So. That is another issue. That is an issue that we have to work on from now on. But we think that our active control system is good enough for most of the situation that we have to face.
Okay, thank you.
谢谢。
Thank you very much. So may I start?
Yes.
We are the University of Tokyo team, and our presentation is about the new design concept of ocean current power generation system. So in this demonstration, I want to show you three aspects of our innovation. First one, this is the experimental scale of our new design concept. As you can see, the turbines are rotating opposite direction of each other. The flow is from this side, and the turbine is rotating. So this is an experimental scale, and this is 1/50 of the full scale that we are thinking.
So which one actually drive the generator?
Both. Because they're rotating, so both of the forms are generating power. That's and
How do you keep this device floating?
This is heavy, but we have buoyancy. We have air inside, so this system is buoyant. So we have buoyant upwards, and we have mooring system that tensions downwards. So this stays in 50-meter depth, where the current is maximum. So this is 1/50 scale. So the real scale would be 44 meters diameter for 1 megawatt system.
The ratio is so high. Under the water.
Yes. So that's the reason why we keep it 50-meter depth. If we go further deep, it would be the system would require more materials. And 44 meter is 1 megawatt. But it seems very large. But if you imagine a wind turbine, 1 megawatt is 80 meter diameter. So this is very compact, very small system, which makes it very cost efficient.
40 meters is just the length of the blade.
The diameter. Yes. And these are pictures. This is a picture of the experiment. We told the system to make the current, and as you can see, they're rotating in the ocean as it's floating. So this is you can see the force is balancing.
How many megawatts?
It's in a tank experiment. We have a tank in our university.
What's the
material. The pod is made of iron, and the blade is made from CFRP, carbon fiber made with plastic. So it's almost the same as wind power generation. It's not so heavy. This is heavy, but sorry, I don't have the material. It is buoyant. So if we put it in
And the pitch of the blade is fixed, right?
We control it.
You control the pitch.
We control it. And we have some pictures about it. So we use the pitch control to do two things. For one thing, pitch control is used to maximize the efficiency of the wind due to the wind speed. And one more thing, we change the pitch control to actively control our position of the system. So that's another thing that we do. We have a picture of that too. So by changing the pitch angle, we can move the device to wherever we want it to be. So since we have only one single mooring system, we have, in order to make the system stable, we try to actively control our parts.
If the diameter of your blade is like 40 meters, you cannot put it in 50-meter seat.
Oh, no. I'm talking about the system is in the 50-meter depth and the seabed is 1,000-meter depth. So,
50 meters from the surface.
From the sea surface. The seabed is 100 meters.